look at an example. And we're going to make a scatter diagram. We'll do this one by hand because it's pretty easy. So that's what we were doing yesterday. We know that we have to plot all of our points. And I didn't even tell you what x and y stood for here, but my x's, we have 0 through 6. Okay, so I could try to plot my points 0, 5.8, 2, 5.7, 3, 5.2, 5, 2.8. Six, 1.9, and 6, 2.2. All right. Now, if I asked you to try to find an equation for this data, what would you do? Think back to your Algebra 1, Algebra 2 days when you had to make a line of best fit. How did you draw a line of best fit? Did you just put any random line up there and say it was good enough? What did you look for? I mean, if I did this, is that a good line? Why? It doesn't touch any of the dots. Okay, what if I did this one? Touches a couple dots. Is that a good line? It's better, but I have points above it. Do I have any points below this line? So it's probably not great. So what you kind of look for is a line going through the middle with roughly the same number of points above and below. Those were kind of the guidelines that you guys were given. Now, it's kind of tricky to do that because it's hard to make it perfect. And we don't have a clear measure of which points are the best ones to put on our line. But let's say I wanted to try to write an equation. So I do a couple points here. So it looks like the line I drew went through the point 2, 5.7, and 6, 1.9. So if you wanted to write an equation between them, what would you do? Yep, slope y2 minus y1 over x2 minus x1. So we get a slope of negative 0.95. Okay, plug into y equals mx plus b. So put in your y, what's our m? So we have an equation. If I asked you to use your equation to predict y when x equals 3, what would you do? We have our line, and so we could use this to make predictions if you plug in your x value. And I would get 4.75. If you look back at the table, we did have a point when x is 3. Did we get the same y value as the table? No. Why? Right. Our line isn't perfect. And there's not even a single line that every point would fall on. So, first of all, our line probably isn't great. But second of all, even if it was a perfect line, every point is not going to be on it. So the idea, when you draw a line of best fit, we want the point that kind of minimizes the error to be, so all the points are as close to it as possible. And that's the true least squares regression line. The difference in what the actual value was and our predicted value is what's called the residual. So maybe even easier if you don't like writing down in words, our residual is the observed y minus the predicted y. Okay, observed, that's what really happened. If you're looking at your actual data, the actual value we had. Predicted is what our equation would have said. This is on your formula sheet. So anytime I ask you to find your residual, you can look right there and it tells you exactly what you need to do. So if we want a good line, we're trying to make all of those residuals as small as possible. If we want to do our example, when x is 3, what was our observed y, the real y value? And what was our predicted y? So our residual was 0.45. Right, so if I ask you to make a line of best fit, or it's usually called a least squares regression line, that's the line that makes your residuals as small as possible. Residuals can be positive or negative. Positive means the real value was above what we predicted, and negative residual means the true value was below what we predicted. There is a formula for finding our least squares regression line. So it is just a line. It's typically called y hat for the regression line. And it's just a y equals mx plus b. But there's formulas for these. So your slope is r. Where have we seen r before? The correlation coefficient from yesterday. Times the standard deviation in y divided by the standard deviation in x. The y-intercept is the mean of the y values minus your slope times the mean of the x's. This again is all on your formula sheet, so it's just a matter of being able to use the equations. Most of the time, we'll just use our calculator to get it, but like we've done before, I'll probably have you do one by hand just to see if you can understand the formulas and what they are asking for. So I think yesterday, does anybody have their handout from yesterday close? We did a set of data. We found the R. We worked through that one. We got a slightly different value when we did it by hand versus on the calculator due to rounding error. What was it? -2. We have a set like this. I want to try to write the regression line for that. So I know I'm having you look at that example because we found a lot of this stuff yesterday. I don't remember, did we write it all down? So our R, let's use the R we found on the calculator because it was more accurate. What did we get when we did it on the calculator? and we had the mean and standard deviation for both variables written down. So the mean of the x, we had 4, the mean of the y was 10, standard deviation for x's, and standard deviation for y's. Those all the same values we had written down. Okay. So if I want the regression line, we need a slope and a y-intercept. If you look on your formula sheet or what we just wrote down, the slope is found by doing the R value, the correlation coefficient, times the standard deviation in y divided by the standard deviation in x. Negative 2.1667. And the y-intercept from the formula we wrote down is the mean of y minus our slope times the mean of x. So our prediction equation, or regression line, dy hat equals negative 2.1667x plus 18.666. Do you guys understand how we got those calculations? So this is all stuff we could find by hand. We can get a mean by hand very easily. Standard deviation, it's annoying, but we can do it by hand. You have to make the table. The R was very lengthy by hand, but we've done it. However, it's just not practical to do all this by hand when we have a calculator, so that's what we're going to rely on more often. So let's look at one and try using our calculator to do that. So here is a golf example. Okay, we have, these are the x values and our y values. So let's enter those in our calculator. We all have our data entered. So then if we go into stat, calculate, and we're going the same place we went yesterday, the linear regression, you'll notice there's 2 of them on here, 4 and 8. Technically it doesn't matter, but you'll notice they flip the order, and 4a is your slope, and if you go to 8, b is the slope, so just be careful. I always go with the first one. It's the form we're used to, y equals mx plus b. Your x list should be L1, your y list should be L2. Calculate. All right, does everyone have all of this showing up? It tells us at the top y equals ax plus b. You should have an a and a b. If you're not seeing the r and the r squared, remember yesterday I said you had to have those diagnostics turned on. So if that's not showing up, you need to turn on your diagnostics to get there. Anybody need help with their calculator? So then our regression line, we call it y hat. Okay, a is our slope minus our y-intercept. If we wanted a visual for what this looked like, we could use our scatter plot. So you guys remember yesterday we had our calculator graph scatter plots for us. If we go to the calculator and go to your y equals, okay, make sure your plot 1 is turned on and it's set at scatter plot. And then for my first equation, I'm going to type in this line, 3.1661x and if we do zoom number 9, remember that takes us there, so we should see our scatter plot and the line, and we can see that it's a pretty good line for the data. It's not perfect because that data wasn't perfect. There is no exact line, but this is the best one. Did we get that? Next question I asked. Predict the distance the golf ball will travel when it's hit with a speed of 103 miles per hour. So 103 is which variable? X. So you just plug that into your equation. And you get 270.3 yards. Everybody getting this?
It's stuck on.
Okay, hit second on. Just turn the calculator off and turn it back on. It should work. Sometimes they get frozen. Okay, last thing I want to do here, next to last, find the residual. So how do we find the residual? Observed minus predicted. Our observed is the real value. So when it was hit with 103, we had a distance of 274 minus our predicted 270.3. So we get a residual of 3.7 yards. That means our line is off by 3.7 for that particular line, so not too bad. If I ask you to interpret the slope and y-intercept. So the slope, y equals mx plus b, the m, that's change in y over change in x. Right? Y was in yards divided by, so per miles per hour. So it is saying that the ball will travel 3.1661 yards per mile per hour. So if you hit it 1 mile per hour faster, it would travel an additional 3.1661 yards. Okay. The y-intercept. That's where you hit the y-axis, so when it's like x equals 0, it's like our starting position here. Doesn't always make sense in the context of the problem. You know, does it really make sense to say your ball started at a negative 55.7966 yards? No, but that's the formula that's needed for the equation to be accurate. that is really the end of this section. One thing I do want to caution you, do you think this equation would be good if we used, let's say, a machine that hit the ball 300 miles per hour? Why would this not be very accurate then? Okay. R is not resistant. Extreme values throw it off, doesn't it? If we look, do we have any x's close to 300? No. So you have to be very cautious. This line is a good model for x's that are similar to those. But if you have an x that's very far off, it is not going to work. Sometimes they call that outside the scope of this model. This equation wouldn't make sense in that instance. It's only applying to things close to it.